All right, guys, welcome to another episode of CUDA Education. I am doing this video right after the Ray Tracing 10.1. So my Ray Tracing 10.1 video is the whiteboard edition of this algorithm, which basically discusses the entire algorithm, right, on the whiteboard. So this video is now following up on that video where I am going through, um, I'm going through, I'm going through sort of the behavior of the shaders that we have. So if you guys want to join in on the fun, tutorial number 1 is installing the Vulkan API on a Windows-based machine with a Vulkan-capable GPU. Tutorial number 15 is installing all of these examples. If you want to be able to run the ray tracing examples, which are all these ray tracing examples here, you need to be able to, you need to make sure your GPU is ray tracing capable. For NVIDIA, its RTX cards are greater. I can't talk about the other GPU vendors, okay? But let's get into it. So if we run our algorithm, we basically get spheres which are procedurally generated mathematically. We could see that the edges of the spheres are very smooth, which is what we want because we're not using triangles or anything to create the edges. We are, or meshes or anything, we are organically generating the spheres from a mathematical equation, which is kind of what we want. We don't want to artificially create something from triangles. We want to mathematically generate it, right? So it's more efficient. It's better for the GPU, less resources. We don't have to manage memory as much because, you know, it's just an equation. Okay. So in the whiteboard edition, we had a big discussion about the shaders, right? So we have our intersection shader and we have our hit shader. Okay. Now the intersection shader is the intersection shader is a sort of in charge of recreating the sphere and testing whether as the ray traverses the scene, it hits the sphere. Okay, so intersection shader is basically a mathematical thing, right? We just care about, we have a sphere, we have a sphere intersect function that basically tests, does the sphere and the ray hit. If the sphere and the ray hit, then this number changes. If this number changes, then we report an intersection. Okay, so right now we are reporting intersections. What happens intellectually if I do not report intersections? Now you have to bear with me, guys, because I have to recompile the shader. The shader is an external file, and you have to recompile it into the SPARE-V format. So the SPARE-V format is a proprietary language from the Kronos group, which also creates Vulkan. And the purpose of the SPARE-V format or the SPARE-V language is to ensure consistency of behavior across all GPU vendors. So drivers and behavior will be consistent across vendors regardless of which vendor it is, right? So that was the purpose of the SPARE-V language. So we have to basically take our external file, our external shader, compile it into SPARE-V, and then when we run it, we'll get consistent behavior. Now, if we don't report intersections, what do you think happens? If we don't report intersections, if we're not testing to see a ray hits a sphere, if we're not doing that test and reporting intersections, what do you expect happens? Guess. Okay, if you guess that you get a blank sheet of paper, you are correct. All of these rays that you see, all of these pixels that you see are miss rays, miss pixels, right? So we're just seeing our background color because as far as the application is concerned, all of these rays traverse the scene and it didn't hit anything. And that makes sense because we have disabled intersections, okay? Now, just for sanity's sake, let's put back our intersections. So I have to put back the report intersections function and recompile the shader. So if we start reporting back intersections, what do you think will happen? If we start reporting back intersections, what do you think will happen? We will get back our spheres, right? So just as a sanity check, I'm going to put back the intersection reporting, and we're going to run the file, and we're going to see if we see the spheres, right? Again, you have to compile the shader down to SPARE-V format so that there's consistency of behavior across all GPUs. So we have NVIDIA as a GPU vendor, we have AMD as a GPU vendor, and now we have Intel as a GPU vendor, right? I'm sure there are others that are coming online too. So if we now run our application with intersections being reported, we happily see that we now can visually see our spheres. Now, we have to make sure that I'm going to rehash based on my whiteboard edition. We're going to have to rehash the fact that the intersection shader is purely a mathematical thing. The intersection shader is not generating the spheres themselves that we see in the application. So these spheres that we see, it's not being generated by the intersection shader. That is being generated, the visual aspect of what we see in our application is being generated by the hit shader. Okay, I apologize for the naming snafu, but that's just how the application was built, and I'm not gonna start renaming stuff, what have you. Okay, so intersection shader reports that there was a hit, and because we report that there is a hit, we now can visually see the sphere. But the intersection shader isn't in charge of us visually seeing the sphere. In order for us to visually see the sphere, we have to go to the hit shader, right? And you could sort of notice that, you know, the hit shader is sort of dealing with lighting, it's dealing with position, it's dealing with like the camera stuff, all that stuff, right? So we could see that this hit shader is in charge of actually, you know, visually generating the sphere. Now, I have another question for you guys. What happens if I disable the hit shader? What happens if I disable the hit shader? Now, you have to be very careful with how you answer this one. I'm going to rehash what I said previously. Rays traverse a scene. The intersection shader algorithm tests to see if those rays hit the sphere. Okay? So the intersection shader is a mathematical thing that tests to see if we hit the sphere. So the intersection shader is in charge of reporting whether a ray and a sphere intersects or not. Okay? So that's the job of the intersection shader. The job of the hit shader is to paint the sphere and for us to visually see it. Okay? So we have our intersection shader and we have our hit shader. Now, if we disable the hit shader, if we disable the painter, if we take out all of the logic as it relates to what the hit shader's purpose is and what it has to do, if we take out all the logic and we just kind of blank the hit shader, what do we expect to see in our application? Oh, I should have been compiling while I said this, but all right. Yeah, so what do we expect to happen if we handcuff the painter? If we keep the painter away from his canvas or her canvas? If we keep the painter away from his canvas or her canvas, what do we expect to happen? Now, rays are still traversing the scene. We are still reporting that there are intersections that occur, but we disable the painter. We make sure the painter can't get anywhere near the canvas, and we also take away their paintbrush and their tools and all of that stuff, all their watercolor stuff, everything. We even take them away from the studio, okay? So the painter cannot paint. What do we expect to happen? We have disabled the painter. We have disabled the hit shader. What do we expect to happen? Well, if you guess something like this, you are absolutely correct. What are we looking at here? So we have our rays. All of these pixels is rays. We have our rays. We have miss rays, which traverse the scene, doesn't hit anything, and we get our background color. We have discussed that many times. We also have our rays that intersect something because we have our intersection shader that is reporting intersections. Okay, so we're reporting intersections. Okay, so rays are traversing the scene and the intersection shader is reporting intersections. However, after we report intersections, we don't have any logic. So we're null and void, we're blank, right? When you disable the hit shader, which is mean you're disabling the painter, you get undefined behavior. Usually when you see something like this is Vulkan saying, hey, I have to report that there's an intersection that occurred, right? And you could kind of see that the outline of this stuff is sort of in spheres. Like you could see at the edge that it's trying to make spheres, right? And you could see when we rotate it that you get like different colors and stuff. But this is Vulkan saying, hey, I have to report an intersection. So I'm reporting an intersection to the Vulkan API, but I have no logic to say, how do we display this stuff? So whenever you see Vulkan does this kind of stuff where it's like grainy, you have, different colors as you rotate, all that stuff, that is basically Vulkan like trying to display something, but it has no formal instructions on how to display it. Okay, so we have no formal instructions on how to display it, and as a result we get this behavior, right? And it makes sense because we have disabled any instructions as it regards to painting the spheres. So we report an intersection, we know that there's something there. There's no two ways about it. We know that there's something there. Okay, we could even zoom into the know that there's something there. But as you can see, it gets weird. It gets weird, guys. It gets weird because we haven't provided any instructions for how to visually display an intersection. So if we put back our intersection, if we put back our painting logic, if we put back our hit logic, if we put back our let's visually see the spheres, we will regain back our original application. Okay? And that's pretty much what I wanted to discuss in this video. There's also the mist shader and the regen shader. Let me yeah, so let's rerun our application, and now we have beautiful instructions on how to display a sphere, and we see our spheres here. Okay, so we are in good business here. We are in good business here. So we have our we have our spheres back, right? And it's actually rather beautiful, right? So this is a beautiful application. Shout out to Sascha Willems for creating these applications. It's actually pretty helpful in learning Vulkan. So we have ray tracing intersection, and then just briefly, I mean, I won't play around with it too much. We have our mist shader. So our mist shader is just defining a color. Okay, so if I change the mist shader color to a different color, I mean, yeah, the mist ray color to a different color, I'm going to see in my application that the background color changed. Okay, maybe I do a 1 here too. I'm now compiling the shader just to see what will happen. So this is the mist shader and this is the raygen shader. So the raygen is basically shooting rays into the scene. Trace ray ext is sort of the big guy on campus. This is the trace ray ext is what sort of finally shoots the rays into the scene, and then we could get our so as you can see, guys, because we changed the color of the mist, so all of these rays are mist rays. So because we change the color of the mist rays, we now get a different color for when a ray traverses a scene and it doesn't hit anything. Nice color, actually. Let's do 0 here. Let's do 1 here just to have some more fun. I'll recompile, but we could see that based on what we see here, that we change the color of the mist ray. So it's not an expensive operation. You basically say, okay, the ray traversed the scene, it didn't hit anything, display this color. You know, nothing too spectacular. Let me just wait for it to compile, and then we will move on to so here we have a different color again because I changed the color of the background. So we have a different color again. Beautiful color again too, right? I know how to pick colors, but yeah, we could see that the color changes because the mist rays are marked a specific color, right? So we're not, it's not, let me put it back to the original value, so we're good there. Now, we also have our ray gen. I guess with this one, we could just say, okay, what happens if we don't generate any rays in our scene? This is an easy one, guys. What happens if we don't generate any rays in our scene? What happens if we do not generate any rays in our application? If we don't generate any rays in our application, then blank, what? Pretty easy one. So finally, you know, after much pain and suffering, I now have a full understanding of why there is an intersection shader. In the other ray tracing examples, generally speaking, in the other ray tracing examples, we have a ray gen shader, we have a mist shader, and we have a hit shader, but we don't have an intersection shader. And I was like, why is it that for this procedural geometry application, why do we for this procedural geometry application, why do we have this intersection shader? I don't understand the intersection shader. What is the difference between the intersection shader and the hit shader, right? Now I fully understand why. Vulkan natively can't necessarily, you know, it can't on its own sort of see or process procedurally created objects on its own. So it needs these axis aligned bounding boxes to help with, you know, whatever, right? So because of that, we have this extra intersection shader. Now, if we disable the rays going into our application, into our scene, if we disable the rays, what do we expect to happen? We expect to see a very blank sheet of paper. I mean, really blank. This time it's really blank, but we don't even have a background color. That makes sense because the rays that miss are also not being generated. So obviously the rays that hit aren't being generated and the rays that miss aren't being generated either. So we just get a blank sheet of paper, like really blank. There's nothing is being done here. Now, if we put back our logic, in our array tracing, if we put back our logic in our array tracing, if we put back our logic in our array generation scene, if we put back the logic and we recompile the shaders, we will get back our arrays. And once we get back our arrays, we have to categorize the arrays between rays that hit and rays that miss. Again, guys, ray tracing 10.1. If you want a whiteboard edition, if you want to just, you know, I have a whiteboard and I go through all of this stuff that I'm talking about here. So if you're a little bit lost, don't despair. So we get back our spheres, right? Because we now have miss rays, we now have hit rays, and we have a beautiful application. We have our painter that paints, and we have our intersection friend that basically, you know, tests to see whether a ray has hit a sphere or not. So just real quick, you know, the axis aligned bounding boxes, you know, it's not gonna test to see if a ray hits a sphere out here, right? It's not all of these pixels that you see out here. It's not gonna test, right? And it's not gonna waste computation trying to test to see if a sphere hit in these regions, right? Because it's not near it didn't go through an axis aligned bounding box. But for these guys here, it's going to test. You see, it's going to test. And that's pretty much it, guys. I'm gonna keep going with this stuff. If you guys want to follow along, you need to have running code on your machine. Um, I strongly suggest that get tutorial number 1, which is installing the Vulkan API on your Windows-based machine with a Vulkan-capable GPU. Tutorial number 15 is installing these examples. If you want to run the ray tracing stuff, you got to make sure that your GPU is not only Vulkan capable, but it's also ray tracing capable. For NVIDIA GPUs, it's RTX and above, right? RTX and greater. I don't know about the other vendors, right? I have an RTX GPU on my system. All right. Shout out to Sascha Willems, who created all these examples. I think the next one that I want to do is probably ray reflections, right? But you got to wait for the next video to see what that's all about. Ray reflection. So we're reflecting rays, and like it's almost like a mirror, okay? And we're trying to see what's going on with that. But that's going to be for the next video. Thank you guys for watching. You know what to do about YouTube. Support the channel. Get your friends together. If you're artistically inclined, or if you know someone that is artistically inclined, an artist, someone that's into graphic design, into visual design, into data visualization, informatics, all of that stuff. You need to be able to put pixels on a screen, and you need to be able to display stuff digitally, right? We are in the digital age now. There's no question about it. This is an excellent skill to have. So please support the channel. You have the series. There's a whole Vulkan series too for just creating a triangle. It's not this triangle. It's a different triangle, but creating a triangle. But I've been focusing on the ray tracing stuff, right? Because that's like the big cool thing to do now. The reason why we do ray tracing is because it's more naturally it's more true to realistic, photorealistic sort of visuals. So the problem with video games and animation and things of that nature is that it's a lighting. So you can't artificially, but before ray tracing, people were artificially trying to simulate what happens with the light. But if you could just ray trace a scene, and the light rays bounce and mix, and you have shadows and everything, you know computationally, because you're just basically shooting rays into a scene, and wherever the rays goes and wherever the rays blend is what actually you're actually showing. Then your graphics becomes photorealistic, right? And that is the whole big deal of ray tracing. So I've been focusing on that. I will eventually get back to just all the other examples. Vulkan, you could also do compute. So Vulkan it's a GPU programming language. It's not just focused on computer graphics. It's basically focused on programming your GPU. So you could do parallel processing, high performance computing, all of that stuff with Vulkan. So at some point in the future, I will dive into that stuff too. But right now, I just want to get through all of the ray tracing examples. I've already done ray tracing basic. I'm now on ray tracing intersection. I'm going to do ray tracing reflections. Um, and just understand there is a main algorithm, and then there are shaders, external shaders that you have to compile into SPARE-V format, so the application knows what it wants to do, or has instructions for what it wants to do for different events in the application. The reason why these shaders are external files, from my humble perspective, I don't know if it's the official word on it, but from my humble perspective, the reason why these shaders are external files and all that stuff is because you want to be able to slot out one shader for another shader. So you want to be able to basically say, okay, I want one shader to do this, and I want to quickly change. I want to point to a different shader to do something else. Actually, let me I'll do it for another video, but remember I discussed also the intersection shader being in charge of mathematically creating the testing for the sphere. So if we change the intersection shader, if we change it from testing a sphere to testing a cone or testing something else, we will get a different shape. Let me not do it in this video just because I've kind of concluded the video and I've discussed, but the intersection shader is testing the shape, so in this case a sphere, against the rays. If we want to change the shape that's inside the axis aligned bounding box, we have to do it with the intersection shader, but I'll do that for another video. All right, thank you guys for watching. Have a great day.